So today we're going to be talking about the random effects estimator for the random effects model. So we had previously talked about the application of all the estimators for the pool model. We also talked about the application of the fixed effects estimator for the fixed effects model. And today we're going to be talking about the application of the random effects estimator for the random effects model, which happens to be the preferred estimator if all the assumptions are satisfied. So let's talk about today the random effects estimator for the random effects model. So before, as sort of introduction, the fixed effects model can be viewed as applying only to the units of a study. Remember, applying only to the units of study. So remember, one way to think about that fixed effects estimator is that we estimate an intercept, for each of the units. So, that intercept applies to each specific unit. So, but some other cases, let's say we had fixed effects estimator and the units are the countries. So each of those intercepts is going to apply for each specific country. So, and this is a limitation for prediction, outside of the units of the study. And the random effects model does not have that limitation. So this is a limitation for prediction. For prediction outside of the units of the study. Yeah, so the random effects model is not going to have that limitation. It's kind of like a more general model. So the random effects model does not have that limitation. So that's kind of like an advantage of the random effects model relative to the fixed effects model. So the other, however, usually there are trade-offs. Remember, in the random effects model, we're going to have to assume that the unobserved individual effects are not correlated with explanatory variables. So that's kind of like a limitation relative to the fixed effects model. So we need to assume that unobserved individual effects are not correlated with XIT. Okay, so that's kind of like a limitation. So I'm going to write down the model again. So remember the way that we describe it. We have XIT, the dependent variable, the vector of explanatory variables, and then we have, remember we have the mean of unobserved heterogeneity. So we assume that we have a constant intercept, mean of unobserved heterogeneity. we have these individual specific random effects. Individual specific random effects. Kind of the way to think about that, we have errors for each individual in particular. We have that random effects for each individual. And these are the regular, I call them regular errors. In the literature, they use like a more sophisticated name. They call it idiosyncratic. These are the idiosyncratic errors. And the way I think about it, it's like the regular error term that we have for each individual in each time period. That's kind of like the regular error terms that we have. Remember, so that's our random effects model. So this is mean of unobserved heterogeneity. I guess I should have said across. So this is across the individuals, and these are individual specific random effects. And notice that these effects are time invariant. Okay? They are for each individual, but they don't change through time. On the other hand, the idiosyncratic error terms, those are error terms that change for each individual and across time periods. Okay, so that's in generally the description and kind of how does it compare to the fixed effects model. The other thing that I should mention, and I'm not going to write it down here, is that in my experience, the random effects model tends to be like a more efficient model relative to the fixed effects model. Okay, so that's kind of like another advantage. And you will see, probably it's due to the fact that we use these generalized least squares, which is more robust than in the case of the fixed effects estimator, we tend to use just OLS. Okay, so what are the assumptions for the random effect model? Give me sometimes. So what are the assumptions for the random effects model? Okay, so and you have this handout. So the first assumption is that we have exogeneity. So the other thing is, now remember, have in mind that we have two errors. So we're going to assume homoscedasticity, and that's going to be the variance of the errors of the idiosyncratic errors, and also the variance of the individual level errors are also, those variances are constant. So we have this homoscedasticity for all those errors. And then we have also this independence or correlation. So the first type of independence is going to be between the error terms. So these are going to be the error term for individual I, and time t is going to be uncorrelated to the error term of any other individual. And actually, something that I should mention is that, so note here that we're not excluding also, this property is very general. Okay, so whereas we have individual I, the error for individual I in time period t, and then we have this error for individual j, this condition also works when we have here the error for individual I. Okay, so this is very general. So in generally, the idiosyncratic errors for any individual in any time period are not correlated with individual level errors, even for the same individual. So the second kind of independence type of assumption, is related to the error terms for each individual. And of course, the errors of one individual in time period t are not correlated with the error terms of another individual during the same time period or at different time periods. Okay, so that's kind of what that assumption is all about. So, the errors are independent, between individuals during the same time period and also in different time periods. And also the individual level errors are independent from each other. Okay, so those are the three type of independent assumptions. Things get a little bit more complicated here in terms of kind of this autocorrelation type of assumptions, due to the fact that we have two types of errors. Now, one way to think about the random effects model is a model. Sometimes it's called like an error components model, because we can use this eta. You can think of this composed error term eta as the sum of the idiosyncratic errors and the individual level errors. So that's like just one error term, and the variance of that combined error term is going to be equal to the variance of the individual errors. I'm not going to prove you here, but remember, this result here is due to the fact that we have those independence assumptions. Due to the independence assumptions that we discussed previously, because those errors are not correlated. So the variance of basically here, the way to think about this thing is going to be the variance of these two errors is equal to the variance of each individual error. There are no correlations. Also, the covariance between these eta terms is going to be equal to the variance of only of the individual level errors. And again, you can prove that. So that's again due to the assumptions of the model. And so let me see here. So this is the correlation of the errors for the same individual across different time periods. Okay, so that correlation is given by the variance of the individual level error. And now, of course, the correlation of these eta error terms for different individuals in different time periods is going to be equal to 0. Okay, this is also due to those independent assumptions. And if you want, you are welcome to try to prove these results, which are they are a direct application of the assumptions that we had talked about previously. Okay, so those are the structure of the errors of these error terms. So for the T observations, so let's assume that we're only interested in the unit I. So let's have the vector of these eta errors. Okay, so it's for individual I during all the time periods, and let's see what's going to be the covariance metrics of the errors for the I individual across all time periods. So it's going to be the expected value of the product of this vector, of the transpose of this vector times the vector. And if we do that using the previous results, we're going to end up with this sigma I matrix, where we have in the diagonal elements are going to be the sum of the variances of the errors, and the off diagonal we're going to have the variance of the individual error term, and this is based on this result here, because if you think about here, the variance, so that's what we have in the diagonal. Okay, and off diagonal we have those correlations which are given by the variance of the individual level error, and that's kind of reflected in this omega I matrix. But of course, these variances, we assume that we have homoscedasticity, so this sigma I matrix is basically a constant, and with that we can build the variance covariance matrix of dimensions nt times nt. So, and that's the variance covariance matrix of the errors for all individuals during all the time periods. Okay, so this is our omega matrix. And of course, once we have this omega matrix, we can think of the random effects model as a generalized linear regression model. So here the conclusion. So the random effects model is a generalized linear regression model, because the variance covariance of the errors has this specific structure, which we have it in omega. Okay, so hopefully that's clear. That gives you an idea. So basically, given these assumptions of the random effects model is a generalized linear regression model. So once we know that, of course, then, so since the random effects model is a generalized, or can be viewed as a generalized linear regression model, or fits within the definition of a generalized linear regression model, work on this thing, generalized linear regression model, then the best option for estimation of the model is going to be feasible generalized. This is going to be the feasible generalized least squares estimator. Okay, so the feasible generalized least square estimator, and I'm going to call it B, which actually is the random effects estimator. So it's the same thing. It's just going to have the structure of the feasible generalized least square estimator that we had described previously. Okay, so since we have panel data, and I have mentioned this before, this can be rewritten using the matrices for each individual I. And here we can have that omega variance covariance matrix. So there's two ways to write the estimator. Writing it this way, it might make estimation easier, since this X matrix, since we have T times N, that can end up being like a very large matrix. So using this second, so this can work, but using the second formula might make things a little bit easier. So remember that we are calculated the inverse of this very large matrix. So here this matrix is NT times NT, and here we only have the inverse of a T by T matrix. Okay, so estimation of this second using the second formula might be easier. Also, remember the other way in which we can go about estimating the generalized linear regression model is by using this transformation that we actually discussed when we were proving that the generalized least square estimator is the best linear unbiased estimator for the generalized linear regression model. So we discussed that estimator. Basically, you have to pre-multiply, you have to transform your data using the Koleski decomposition of this omega matrix, or the Koleski decomposition of the sigma matrix. Okay, so that's the other alternative. So you can use or you can use OLS on transform data. Then using the Koleski decomposition. Well, so I'm gonna write, so remember, you're saying it's kind of like the square root of that matrix, but it's not really the square root. Remember, that comes as the Koleski decomposition of that matrix. Okay, but to simplify things, I'm gonna write it anyways. This estimator is very easy to use, so most of the time, probably you won't need to use this transformation. Now the next question could be, okay, so to apply this estimator, notice in general, to apply the feasible generalized least square estimator, we need an estimate of the elements of this variance covariance matrix of the errors, because so this is sigma, and most of the time we don't know sigma, so we need to estimate the components of sigma. We in this case are going to be these elements, the variance of the errors, sigma mu square and sigma epsilon square. So how is that we go about estimating that? So let's discuss that. So how to estimate, and there are different procedures so to go about estimating. So I'm going to describe one so that you get a sense on what are the steps involved on that. So basically, asking how do we estimate the sigma, the omega, or the sigma, 1/2, or the square root, is the same as asking ourselves how to estimate sigma mu hat square and sigma square. Okay, so it's the same question. Okay, so let's start with the the variance of the idiosyncratic errors. So to do that, what you can do is you can first estimate, use fixed effects estimator from the fixed effects regression of yit minus yi dot on xit minus xi bar. We obtain, so that regression will give us an estimate of the variance of these idiosyncratic errors. So this is just and I'm calling that within. So those are the errors of this within that we obtain after estimating that fixed effects regression. It's going to be divided by n t minus k n t, let me see, minus n minus k. Okay, so and I goes from 1 to n, and t goes from 1 to t. Okay, so what's going on here? Just to give you some intuition, so this error term, is going to use the observed values of the dependent variable minus the predictions, which are obtained by multiplying the explanatory variables times the coefficient used with the within, or what we call the fixed effects estimator. Okay, so what's going on here? So kind of the intuition here, and hopefully the way to think about it. So remember here that what we had to do was to apply the fixed effects estimator on a random effects model. Okay, and here I'm just gonna remind you how do you go about doing that. So let's start with the original random effects model, which is given by YIT equal to alpha plus xt prime beta plus mu I plus EIT, and I run out of space. Okay, so remember, and then the next step, we need to calculate the between transformation, okay, for this random effect model, and that would be yi dot, this is kind of like a digression, this is going to be equal to alpha plus xit beta, and so this should be a dot there. Okay, and then here we should also have the average of those error terms. So notice that the alpha and the mu I, those are constant, so the average is going to be the same thing. And then we can calculate, or we can come up with the fixed effects or within effects transformation. I guess we call it that the within transformation for the random effects model. So the within transformation for the random effects model, we just subtract 1 minus 2, so we're going to end up with YIT minus YI bar, so it's going to be equal to, so the intercepts disappear, those individual level errors also disappear. Okay, so and then we also have this component of the error term. So the idea here is, you see, when we apply this estimator, basically kind of what's going on here is that we get rid of that individual level error. So the only component that we have are these components related to the idiosyncratic errors. So that's what that allows us to estimate the variance of just related to the idiosyncratic errors. Okay, so that's kind of like the way to think about that. Okay, so what about now the error for the individual level? So the error for the individual level errors. So to estimate the variance, so we can obtain it from the between regression of yi on xi, whose error term variance is so this is kind of the theoretical square. Okay, so that's the variance for the between regression. And once we have this variance, we can obtain sigma mu square from the variance of the between regression. Okay, and in a second I'll show you kind of what's going on. So remember that in the well, again, so what I'm going to do again, so let's start for the between regression of the random effects model, we will have to start with the random effects model. Yeah, so the between transformation, I had already done it before. So that's original random effects model. So this is the between transformation. Alpha plus beta plus mu I plus E I. Okay, so this error here, remember, we call it eta, so this is going to be, it can be called ni dot, so that's kind of like the eta error. So let's write it down. I mean, what's that thing? Decompose that error, so that's going to be equal to mu I plus the average of those error terms divided by t. So remember, that's by definition that ei dot bar, so that's what we have that, and then the variance of eta I dot is going to be equal to the sum of the variances. Now here, once again, we make use of that property that we know that all those errors are uncorrelated. So in fact, due to that correlation, the variance of the sum of all those errors is just the sum of the variances. There are no covariances, so that makes our life pretty easy. So once we have that, then the variance of ni dot is going to be equal to, we know that theoretical, so this is the theoretical value, plus is going to be, so these are all constant, it's going to be the variance of the errors, the square. Okay. So here's something, let me think about it. So here for the variances, since this is the variance of this term, let me see here what I should have done is the following. Here I'm missing a step, so I'm gonna write this thing down, because what we have here is the variance of the sum of the AITs divided by t. Okay, so since the variance of t, so this is going to be t squared. Okay, and then inside we're going to have the sum of all those variances, so it's going to be t, which are a constant. So if we do that, then we end up with the variance of eta I dot equal to sigma square mu plus sigma e squared divided by t. Okay, so here I guess what I'm gonna do here, so like kind of like a digression, since it didn't flow very well. So this is, remember, so the variance of the sum of the AITs is gonna be equal to the sum of the variances, and since we're assuming homoscedasticity, they're all are going to be constant, so this is going to be equal to t sigma e epsilon square. Okay, so that's kind of how I got that part. Okay, so I think I show you, and of course, so that's the theoretical model. So you see, when we estimate the, we use the between estimator, we end up with an estimate of the variance of eta I dot. Okay, so in practice, to get sigma mu square hat is going to be equal to the variance eta I. It's going to be the variance. That's what we obtain, from that between estimator of the between transformation for the random effects model, minus that error that we had estimated previously using the fixed effects estimator for the random effects model. So this comes from the between estimator, and this comes from the fixed effects estimator. Okay, now, of course, in practice, probably you are not going to have to do this thing because you're going to be using some software, but it's important that you have an idea of where, things come from. I guess, a couple of comments to end this section. So let's go back to the summary models. So, in class we have discussed in detail estimation of the pool model, and we talk about pool OLS for this model. We talk about the between estimator for the pool model. We talk about the fixed effects estimator for the pool model, and we also talk about the first differences estimator for the pool model. We have talked about the random effects estimator for the random effects model, and we talk about the fixed effects estimator for the fixed effects model. So, those are the preferred estimators, and they happen to be preferred because in each case, if the assumptions of each of the models are satisfied, they are going to be the most efficient estimators. So some of you might be wondering, so why we didn't, talk about the pool OLS estimator for the random effects model or the between estimator for the random effects model? Well, so I kind of, for the derivations of that omega matrix, I talk about the between estimator for the random effects model, and also I talk about the fixed effects estimator for the random effects model. Those are the ones that allow us to estimate those variance components. But I didn't talk about the first difference estimator or the other one, the pool estimator. Well, and I didn't talk about that because, first of all, the preferred estimator always for the random effects model is going to be the random effects estimator. And the other thing is, you could derive all those estimators for the random effects model in exactly the same way in which we derive for the pool model. You know that you always start with the model that you are assuming, and then you apply the needed transformation, and then once you have, like for example for the between estimator, once you have the between transformation for any of the models, you can apply the between estimator. Okay, now for the fixed effects model, of course, the pool OLS model, the between estimator, and the random effects estimator, they are all going to be inconsistent estimators. So that's why usually, we didn't talk about those estimators. Now, I know that this is kind of the theory, but you see in practice, in econometrics, most of the time the preferred estimator and kind of the default estimator is going to be always the fixed effects estimator. Okay? Notice that estimator is always going to be consistent regardless of the model that you are assuming. So that tends to be, like the default estimator in econometrics. Now, during the lab, we will learn about how to go about testing to explore which is the model, which is the true model. Here, all these explanations, all these derivations have been done from the perspective that we know what's the true model, but we don't know what's the true model. So, and that's kind of what we're trying to find out. I mean, if we already knew what's the true model, we just go and apply the preferred estimator for each of the of these models, but we don't know. So that would be, I mean, kind of what we do during the lab. But again, in econometrics nowadays, most of the times we use the fixed estimator because it's the most robust estimator, and remember, also has this property that allows those unobservables, time invariant unobservables, the potential to be correlated with the explanatory variables included in the model, which it's important from an endogeneity perspective. Okay, so that's what I have for you today.